Okay, so with these properties of alcohols, the hydrogen bonding allows for the great solubility of these alcohols in the water, and also they're very high melting and boiling points, because as you know, the hydrogen bonding is a great determinant of melting points and boiling points. The other concept that you should recall from our lesson on intermolecular bonding is that as chain length increases, such as we've shown here, excuse me, I'm getting a message here, I apologize. As the chain length increases, as you can see in these three examples here at the bottom, solubility goes down. So, and also boiling point goes up as the chain length goes up. As you can see here, this methanol compared to an ethanol, compared to a propanol, methanol has the lowest boiling point, and the boiling point increases as the chain length increases. And the smaller alcohols here, so methanol, is much more polar than longer chain alcohols, such as ethanol and propanol. So propanol's polarity would be lesser than methanol's degree of polarity. And that's because this electronegative oxygen over here has a greater pull on the electrons coming from this end of the molecule, whereas over here, this OH is not strong enough to pull electrons from all the way down here. And as the chain gets longer, it doesn't have as great a pull on these electrons. So it's not as polar. It's not as great a difference in the polarity between the two ends of the molecule as it is here in this shorter molecule. The next group that we can talk about are ethers. Ethers contain two alkyl groups that are joined together by an oxygen atom. So the general formula for ethers is some part of the alkane group, an oxygen, and then the rest of the alkane group. So two alkyl groups joined by an oxygen in the middle. And ethers can be used, can be named using two methods. And the first method, the longest alkyl is the parent alkane. And the second alkyl is numbered and named oxy. For example, here, methane or methyl and ethyl. So the longer one, which would be the 2 carbon unit, the ethane, that would be the parent alkane. And then this one will be given the ending oxy. So methoxyethane, that would be one way to name this, methoxyethane. The second way is that the two alkyl groups are named in alphabetical order, followed by the word ether. For example, this can be called methoxyethane, or which is what we said in the first one, or it could also be called methyl ethyl ether. Okay. Oops. Where are we? And let's look at another example. Here we have this kind of a structure, and we recognize it immediately as an ether because here you have one alkane branch, here you have another alkane branch, and they're joined by an oxygen in the middle. So you can see it follows the formula R, oxygen, and then R. So the alkane, oxygen, and another part of the alkane. And how you go ahead to number this, you begin by numbering the 2 alkyl chains on either side of the oxygen atom, so that you have a 3 carbon and a 4 carbon chain. And if you were to name this using method 1, this would be called prop for the 3 carbons, prop-oxy, and then the parent alkane, which would be the longer one here, the 4 carbon one, butane. So if you were to use it naming the first way, this would be propoxy butane. Or you could, there's a second accepted way, would be propyl butyl ether. Okay. Now, some of the properties of ethers. Ethers are less polar than alcohols. And you can kind of guess why that may be so. It's because the oxygen group tends to be somewhere in the middle rather than at one end or the other. Ether can bond with water by hydrogen bonds, but not with other ether molecules. I'm gonna let you think about that one a little bit to see if you can see why it can bond with water molecules, but it can't form hydrogen bonds with other ethers. You should be able to understand that from all the talking that we've done about hydrogen bonding and what are the special circumstances under which hydrogen bonds form and what kind of atoms you need present. That should be able to tell you why ethers don't hydrogen bond with themselves, but can hydrogen bond with water. Ethers also have a lower melting and boiling point than similar alcohols. So that if you have 2 compounds that are very much the same, except one is an ether, one is an alcohol, otherwise they have the same makeup, ethers would have the lower melting point and a lower boiling point than the comparable alcohol. And ethers, as we said, are soluble in water, and their solubility will decrease as their chain length increases, as the number of carbon atoms increases. And that also makes sense because, as you can, if you remember, the chain would be hydrocarbon chain, and hydrocarbons are not very soluble in water. So as the chain, the hydrocarbon part gets longer, the molecule becomes less soluble in water. And the ethers are extremely flammable because they have this great, these hydrocarbons attached to them, and hydrocarbons in general are good fuels. They're very flammable. There's a few support questions here for you guys to practice with for ethers and alcohols. And then we're going to move on to 2 molecules that are closely related, and these are called aldehydes and ketones. And aldehydes and ketones contain functional groups with a carbon double bound to an oxygen, a C double bond O. And this is called a carbonyl group. So aldehydes and ketones have this carbonyl group in them, but they're different in a sense where they're in aldehydes, this carbonyl group is always located at one end of the parent chain. So that if you can imagine, this R is the parent chain, however long it is, whatever it is at this end. And this carbonyl group is located at one end. There's nothing else beyond this except just this hydrogen. In ketones, the carbonyl group is in the middle of a chain. So if you have this carbonyl group at the end, you know you're looking at an aldehyde. If the carbonyl group is found in the middle, and to this side you have the chain continuing, to that side you have something continuing, then you know you have a ketone. This is a ketone functional group. This is an aldehyde functional group. And then there's naming conventions for naming aldehydes and naming ketones, which we will cover right here, using your parent alkane name. You drop the E and you end in al. And all of the other rules, the same as you did to alcohols, apply, except that by definition, because the carbonyl group is at one end of the molecule, the carbonyl group is in position number 1, always. So there is actually no need to state the number where the carbonyl group is at. You don't need to say that this molecule is a 1-propanal, because of course it's 1-propanal, because the carbonyl group is always located at one end, and that one end would be your carbon number 1. So in this case, we have 1, 2, 3 carbons. So we know we have the prefix prop. So this is a propane kind of a molecule, but we drop the E and we put the al to name it as an aldehyde. So this is a propanal, okay? Now, in this molecule, for naming ketones, you drop the E and you add -one, and you apply the same rules as we discussed for naming alcohols. So over here, we have 1, 2, 3. Again, we use prop, like we would for propane, except we drop the E and we add the name -one. So propanone, okay? Instead of propane, it's propanone, because the carbonyl group is in the middle as opposed to at one end. And since in this case, this is 3 carbons long, we don't really have to say a number. We don't have to associate a number with this one, for example, because where else would it be? It's a ketone, it has to be in the middle. This is one end, this is one end. There's only really 1 carbon that is designated as middle. It's only a 3 carbon chain long molecule. So it's a propanone. It doesn't make sense to say it's a 2-propanone, because of course, where else would the ketone group be? This carbonyl group, where else would it be? Okay, so some of the properties that we can think about for aldehydes and ketones. Short chain aldehydes, such as methanal and ethanal, are typically very foul smelling. They smell pretty bad. Whereas long chain aldehydes of higher molecular mass are generally very pleasant smelling. They tend to have good smells. The carbonyl group makes these organic molecules polar because of this oxygen, giving them higher boiling points and giving them greater solubility in water. They're very soluble in water than whatever is the corresponding alkane without the carbonyl group. So the aldehydes are more soluble than the alkanes and have higher boiling points and greater solubility in water. And although this carbonyl group that we have in aldehydes and ketones is polar, they have lower boiling points and are less soluble in water compared to alcohols of similar size. And these are not because aldehydes and ketones have no hydroxy group. This is because this is because they have no hydroxy group. And because they don't have this hydroxy group, they don't form hydrogen bonds. So again, we're coming back to the concept of the importance of hydrogen bonds and how the presence of hydrogen bonds allows for formation of these intermolecular bonds and affects the boiling point and solubility of molecules in water. So here we can see that although this carbonyl group is polar, it doesn't have the property of being able to form hydrogen bonds. And the hydroxy group in alcohol therefore has a much more propensity of forming hydrogen bonds. So if we compare the boiling points of these different functional groups, so if we compare a propane, which has just got no functional groups, compare it to a propanol, which is the same molecule, it's just got an extra hydroxy group, an OH group at the end, making it an alcohol, we can see that the boiling point in a propanol is much higher than the boiling point in propane. Now, if we compare propanal, the aldehyde, and compare it to propanone, the ketone, again, we can see that the boiling point of the propanal is lower than the boiling point of the propanone. There are some support questions for you to practice that with. And we're moving on to our next organic compound family. These are the carboxylic acids. Carboxylic acids have this carboxyl group. So the carboxyl group looks a lot like the carbonyl group. So you have a C with a double bond to an oxygen, but then you also have an OH group present. And this group together, this COOH, see, COOH, is referred to as a carboxyl group, a carboxyl functional group. And when you're naming carboxylic acids, you name it based on the longest chain that contains your carboxyl group. That becomes your parent name. And your carboxyl functional group will always be on your first carbon. And you will drop the E in your parent alkane name and add to the ending oic acid. So whatever it is, drop the E and make it an oic acid. Let's look at another example here. For example, we have this molecule and we recognize right away that we have a COOH. And because we have this COOH, we know that it's a carboxylic acid. And we start counting our carbons. So we have 1, 2, 3, 4 carbons. So we know that we have to have bute. And this would normally be a butane. But then because of the presence of this carboxylic group, we drop the E and we add the ending of oic acid. So it becomes butanoic acid. And there's also carboxylic acids. This COOH group can also be found on aromatic benzene rings as a functional group. And the simplest aromatic that contains this carboxyl functional group is known as benzoic acid. And benzoic acid is often used as a preservative in many foods and beverages in order to keep bacteria and mold from growing. You will find the sodium salt of it, for example, if you look on lots of drinks, juices, pop cans, whatever on the back, you'll find that you have this benzoic acid is present in the form of sodium benzoate or potassium benzoate. It's this molecule here that is used as a preservative to keep down the growth of bacteria and mold. Here's some common names for some carboxylic acids and their uses and their origins. For example, oxalic acid is a carboxylic acid that's found in spinach and rhubarb. It's originally found, that's where it was originally purified from. Spinach and rhubarb have lots of oxalic acid. Tartaric acid is, lots of it is found in grapes and in bananas. That's where it was purified from. Citric acid, that's an easy one. We know it from citrus fruit, oranges, lemons, limes, citric acid from citrus fruit. Ascorbic acid, the other name for this is vitamin C. Vitamin C, ascorbic acid, it's found in lots of fruits, lots of vegetables. And then there is acetylsalicylic acid. The common name for acetylsalicylic acid, many of you might know, is aspirin. It used to be used for pain relief, but of course now we have other options for pain relief that don't necessarily also at the same time thin your blood. And so aspirin nowadays is used with caution for pain relief. You don't want to use that very much, especially if you have blood clotting disorders. So yeah, these are some of the common names for some carboxylic acids, which I bet lots of these you've heard of. You've certainly heard of citric acid, ascorbic acid, and acetylsalicylic acid. Now, some of the properties of carboxylic acids are that they are polar molecules. As you can imagine, with this OH group and this carbon with a double bonded oxygen comes quite a bit of polarity. So these are polar molecules, especially since it's at one end, and they are capable of hydrogen bonding. I'm going to let you figure that one out yourself. Why is this capable of hydrogen bonding? And therefore have high boiling points because they are capable of hydrogen bonding. Hydrogen bonding, because you have these intermolecular bonds, it's harder to break them, and you have to put in more energy driving up the boiling point in order to break those intermolecular bonds between these molecules. You have to put in more energy, and that translates to a higher boiling point. And many of these carboxylic acids have multiple functional groups, which also increases their boiling points. There may be other ones or multiple carboxylic acid ends, and that would also increase the boiling point. So that covers carboxylic acids. Now we move on to esters. Esters have this functional group that also falls in the middle of a molecule. So on this side, you're going to have some alkane group, some parent chain, and the rest of another part of the parent chain is on this side. And in the middle, you have what looks like this, which almost looks like a carboxylic acid, except that instead of an H being present here, there's the rest of the molecule. And these are made by the formation between the reaction of an alcohol and a carboxylic acid. So here we have an example of an alcohol. This one is methanol, so methanol, and a carboxylic acid. This one is butanoic acid, so 1, 2, 3, 4 carbons, and then the carboxylic acid tail here. So butanoic acid and methanol, when they react, they form an ester. And this ester is called methyl butanoate. So in this reaction that's shown in this figure is also termed an esterification reaction because it produces an ester. And esters have this, what we talked about up here, showing you it's an RCOOR functional group, where R is the alkyl group, the alkyl chain. And how do you go about naming these esters is that the parent name is derived from the carbon chain containing the carbonyl group. And that name then changes from an oic acid to an O8. So the alkyl group, which is attached to the single bonded O, precedes the parent name. So for example, if you have this structure over here, first of all, you see this, there's an alkyl group on this side and another alkyl group on this side. And in the middle, you have this COO. And there's an R group here and an R group there. So right away, you recognize that this is an ester. And how do you name this? You name it as methyl, methyl propanoate. Okay, so the methyl and then propanoate. So because this 1, 2, 3 carbon part, this propane part, that's the part that has this carboxylic acid. Like if there was no methyl here and there was just an H, this COOH part would be part of this propanoic acid group, right? But because that there's this methyl and here we drop the propanoic and we make it a propanoate. And what kind of a propanoate? It's got a methyl group, so it's a methyl propanoate. So the O8 part is attached to the part that has the carboxylic, the carbonyl group name here. Some of the properties of esters. Esters are quite volatile, even at room temperature. They evaporate very quickly. And they are also present in many waxes and scented candles and lipsticks. And they are very, they have nice odors. They are used in scents and flavors. Oftentimes esters are flavoring agents, or perfumes are often made up of ester compounds. Then there's a couple of questions for you guys to practice with. And I really hope that you guys are using these examples to practice with. Then we have another group, amines, and finally amides. So amines and amides are the last two groups that we're going to be talking about in this lesson. And amines have what is called an amino functional group. An amino functional group are, these amines are typically derivatives of ammonia, and an ammonia molecule is NH3. And an amino group is just, okay, so here's the R, the rest of the alkyl group, the parent hydrocarbon going on this side. And at the end, you have this NH2. And so you can name it based on the longest alkyl that's attached to this nitrogen, this amino group. And that would be your parent alkane. And then you end the, you change the ending to the suffix amine. Okay, so for example, if we have a molecule that looks something like this, and so here is our amino group, our NH2 group here. And so what's attached to this nitrogen here? 1, 2, 3, 3 carbons. This amine has 3 carbons attached to it. So it would be prop. So it would be a propyl amine, right? Propyl amine. And some of the properties of amines are the carbon nitrogen, so this bond here, this carbon nitrogen, and also the NH bonds. These are polar because of the presence of the nitrogen group. And the solubility of these types of molecules goes down as the chain length increases. And as you can imagine, this part of the molecule is not very soluble, right? These are not polar. These are just plain hydrocarbon tails that are not very soluble in water. So you can think that the solubility of these amines, as this would get longer, the solubility would go down. And you can think about that one a little bit more and what it means. Amines are oftentimes very toxic, but they may have some medicinal properties. And Oftentimes, amines have a very foul, fishy type of odor, which is associated with decay and decomposition, something rotting and going bad. That's the smell of amines. And like ammonia acts as a weak base, and because amines are derivatives of ammonia, amines too behave as weak bases. Now, finally, amides. So amides have this sort of a functional group, where the R is a hydrogen atom or an alkyl group. So this is an amide functional group. So you see there is some part of the amide, the group continues this way, and then you have a CON, and then there could be 8 more H's or more longer chains continuing this way, and these are amides. So when you're naming amides, you name the parent acid that contains the COO, like the carboxylic acid part. So this is part of the parent acid. And then you replace the ending of the oic with amide. So for example, if you have something very simple and easy, like this molecule here in example 8, if you were asked to name this amide, you would recognize that, well, this only has 1 carbon. So it would be like a methanoic acid. So, but instead of calling it methanoic acid, it would be a methylamide because of the presence of the amide group. So this would be a methylamide. And some of the properties of amides, they are often used as artificial sweeteners. Aspartame has got an amide functional group in it. It is an amide, aspartame, which is used in a lot of diet drinks and diet sodas, for example. Then we have some support questions that you can practice with for amines and amides. And finally, we have our key question number 6 for this lesson, and this is also due this Sunday, October the 10th. Okay, in addition to key question number 7, whose lesson we'll have on Wednesday, that will also be due on Sunday, October 10th. Both key questions 6 and 7 are due this Sunday, please. And for those of you who have been handing in your assignments, fantastic, good job, good for you. I just want to remind everybody that these assignments make up altogether 40% of your final grade in this course. Another 30% comes from our midterm, and another 30% comes from the final exam. So really, it's to your own benefit to complete these key questions and to hand them in when they're due. This will give you good practice to prepare for your midterms and your final exam, but it also contributes a good chunk of your final mark. So it's really for your own benefit that you should complete and hand in these assignments in a timely manner. Now, right, so let's talk about, just want to take a minute to remind you that we have our midterm coming up, and our midterm will be coming up at the end of our unit 3. And the date that I'm looking at right now is Friday, October the 29th at 1 p.m. So from 1 till 3 p.m. is what I'm thinking of. And I hope that everybody can clear their calendars and schedules and nobody has any conflicts. for the midterm taking place on Friday, October 29th from 1 to 3 p.m. If there's any, if there's something else very important that absolutely clashes with this time, please get in touch with me, email me, check your calendars and let me know so that maybe we might be able to shift this time maybe a couple hours later or and try and find a better time. But Friday, October 29th, after we finished working on Unit 3, is when you'll be getting your midterm exam, which will cover the contents of Units 1, 2, and 3. Okay. Right, so we actually managed to get through this lesson fairly quickly. And I think it's because a lot of this is just things that you need to, these are just rules that you have to understand and follow. And once you understand how to apply these rules step by step, you'll be able to, you'll master being able to name and identify all of these compounds with their various functional groups of alcohols, this hydroxy group, this OH. Amines, carbons and nitrogens form a bond together. Aldehydes, you have a carbonyl group with a hydrogen at the end of a molecule. Ketone, very similar to the aldehyde, but instead of being at the very end of a molecule, it's in the middle of the molecule. There's something else on this side, something else on that side. Carboxylic acid group, where you have this COOH, this carboxylic acid group. It's always at one end of the molecule and it gets the ending oic acid, whatever it is, it's an oic acid, methanoic acid, ethanoic acid, propanoic acid. Esters, where you have this COO, but instead of an OH, there's something else continuing on this side, just like on this side. So this is very similar to a carboxylic acid, but instead of being a COOH, it's a COO, and the molecule continues. So this is an ester. And the way you name it is based on whatever was going to be the name of the carboxylic acid, and you drop the oic and you add an O8. So that, for example, you might be naming it as a methyl propanoate. And finally, amides we talked about, where you have this CO, C double bond O, and instead of it being connected to the next oxygen down here, it's to an amino group here, to an N, and then it could be an NH, or it could be an N and then some more groups down here. And the suffix this gets is an amide. So this could, for example, if we knew that there was three more carbons or 3 carbons altogether here, this would be a propanamide. So all of these functional groups form certain types of compounds, and depending on the functional group that they have, all compounds that have these functional groups tend to have similar properties and turn to participate in similar reactions in very similar ways as other members of their same group. And that is due to the chemical nature of these functional groups. And we will explore in future lessons.
Excuse me, Miss.
Yes.
Can I go to washroom?
Oh, absolutely, absolutely. So, and in a future lessons, we will be talking about just what type of reactions these functional groups participate in, and what are the results of these reactions. So, right, we covered alcohols. We talked about primary, secondary, and tertiary alcohols. And we covered how to name them based on the parent alkane and replacing the ending OL for the alcohol. I'm just using the remaining 45 minutes or so of the lesson to just quickly go over this again. If anybody has any questions at this point, stop me and ask me them. And I can go over it again with you. So, and then you have to make sure that you number your carbons in a way that your alcohol gets the lowest number. We talked about primary, secondary, and tertiary alcohols, where the carbon that has the OH group to it is attached to only one other carbon, attached to two other carbons, attached to three other carbons. And these are examples of primary, secondary, and tertiary alcohols, and then examples of polyalcohols where there's more than one OH group present on your parent chain, and how to name them. And then we talked about how you can also have obviously cyclic alcohols, where you have the cyclic hydrocarbon and the alcohol group attached to it. And this is menthol. This is what you find gives that minty flavor in some gums and mouthwashes, and it's a minty tasting alcohol, menthol. Another example is this molecule of cholesterol. It has a bunch of cyclic hydrocarbon groups attached together, and one of them has got this hydroxide group on it. It's a cyclic alcohol called cholesterol. That OL ending is the giveaway. It's what indicates to you that there is an OH group present. And then you can have phenol, which is this aromatic ring with the hydroxy group on it. Again, the OL ending is what is the ending for any compound that is an alcohol that has an OH group on it, will end in an ol. So menthol, cholesterol, phenol, pentanol, all of these, are alcohols. They have a hydroxy group. And of course, properties of alcohols is they're extremely flammable, they're poisonous. And we talked about the importance of hydrogen bonding and the role it plays in solubility and how it affects melting point and boiling point. And again, also how the presence of the length of the chain, how many additional hydrocarbons is attached to that hydroxy group, how that affects the melting point and the boiling point and the solubility. Again, all of this has to do with intermolecular forces and hydrogen bonding, and how those affect as boiling point, as the chain length goes up, the boiling point also goes up. And I want you to think about why is it that as the chain length goes up, the boiling point goes up. Anybody want to take a guess at why is it that as the chain gets longer, the boiling point gets longer, gets higher? Anybody? Who have we got?
Maybe because like more electrons, and the other one was.
Yep, you're on to the right onto the right chain of thought. Yep, more electrons. What kind of intermolecular forces are we talking about when we're talking about long hydrocarbon chains? Do you remember? Does anybody remember from our couple lessons ago and when we were talking about intermolecular forces, what type of intermolecular forces would this part of the molecule, this part that is not polar, participate in? So it won't be dipole-dipole, because dipole-dipole needs some polarity. I mean, there is some dipole-dipole interactions here, but typically when you're talking about hydrocarbon chains, it's mostly those London dispersion forces that are in play. So if you can imagine, the longer this part is, yes, there's more London dispersion intermolecular interactions happening. And that's why you get this longer, this higher boiling point. Okay. Then we continue to talk about ethers. So ethers, we talked about the properties of alcohols, very flammable, highly poisonous. Ethers are also extremely flammable. And as you can guess, they are kind of reminiscent of alcohols, except instead of an H group at this end, there's another alkyl group. So it's instead of an OH, it's an OR group. And so in some ways they are similar. They're extremely flammable. They're also soluble in water, but they're less polar than alcohols. And they can form these hydrogen bonds with water, but not with other ether molecules. So these ether molecules have this OR, have some alkyl group where you would normally find the H in an alcohol group. In ether, instead of the H, you have some hydrocarbons present. And then we talked about there's two different ways of naming them. Really pick whichever one makes most sense to you. I kind of like the ease of just naming the two ethyl groups and then putting the ending ether, methyl ethyl ether, propyl butyl ether. That kind of seems pretty easy to me. But also you could call it methoxyethane or propoxybutane. Then, oh yeah, finally, aldehydes and ketones. Remember, these two are very similar kinds of functional groups. They're both CO, but instead of H for the aldehyde, you have R for ketones. In aldehydes, this COH group, this carbonyl group, is always at the end of the molecule. Like here in this example, it's at the end of the molecule, whereas in ketones, it's in the middle of a molecule. So you can imagine you can have other ketones where instead of just being this very simple, just CH3s at the ends, it could be longer chains, right? But if the CO group is in the middle, it's a ketone and it gets an ending of -one, okay? And the way you name them, whoops, excuse me, is you just go on and count how many carbons you have, count. If you have 3, if you have 4, if you have 5, if you have 5, it would be a pent, and it would be a pentanal or a pentanone. Those would be examples of how you would name aldehydes and ketones. Very, very straightforward, very, very easy. And talked a little bit about the properties of these. I won't go over these again. You can review those yourselves. Then we talked about carboxylic acids and the COOH, the carboxyl group. So in aldehydes and ketones, we have what is called a carbonyl group. The CO is the carbonyl group, this carbon oxygen. Carbonyl group, but in carboxylic acids, we have a carboxyl group, COOH. And COOH always is at one end of the group. And that end always becomes carbon number 1. And the way you name it is you count your carbons, figure out how many carbons, pick the correct suffix that's associated with this number of carbons. And then you drop the E and you and put in an oic acid. For example, butanoic acid for 4 carbons, pentanoic acid for 5 carbons, hexanoic acid for 6 carbons, so on and so forth. And of course, carboxylic acid, this carboxyl group, can also be attached to aromatic rings, to benzene rings. And in this case, you can have benzoic acid, which we mentioned is a great preservative. It's a very common preservatives used typically in acidic foods and acidic drinks, beverages, sauces, what have you. There's a certain amount of benzoic acid always found in there to keep the bacteria and mold at bay. We talked a little bit about carboxylic acid properties, such as hydrogen bonding and the polarity of the molecules, and the boiling point. I also have high boiling points. We talked about ethers and COO, and continues with an R. So again, you can see how we are kind of building on the concept. So we talked about carboxylic acids with the COOH, see, COOH, carboxylic acids, and ethers, it's kind of like that, except instead of the COOH, it's a COOR. It doesn't end in a hydrogen, it continues. There's something else beyond this other hydrocarbon groups continuing. And the way these esters are made is from the reaction between an alcohol and a carboxylic acid, and that's what produces the ester. This is called an esterification reaction, which we will cover in greater detail, might be next lesson. And how do you name them? Again, you take the parent group, the parent group that had that carbonyl group on it, and you add the ending from, change it from oic acid to O8. Okay, so instead of being butanoic acid, it would be butanoate because it's an ester. And we talked about this example of, so if you were to ignore this part of the molecule and just focus on the part that contains the carbonyl group, you would see that, okay, it's 1, 2, 3 carbons. So it would be a prop. And if this was a carboxylic acid, it would be propanoic acid. But because we see that it's not propanoic acid, there's another methyl group here, there's some R group here, whatever it is, we change it to propanoate, but we need to add in the methyl in front of it. So it's a methyl, or maybe it could be an ethyl, maybe it's 2 carbon groups here, or 3 carbons. So it could be a methyl propanoate. If it was 2 carbons over here, it would be a ethyl propanoate. If it was 3 carbons, it would be a propyl propanoate, so on and so forth. And you base it based on the parent containing the carbonyl. So so that was esters. We talked a little bit about, we'll go over properties of esters, very volatile, and they smell nice usually. They're used as scents and flavoring agents. And then amines and amides. And we'll just go over these one more time, and then we'll probably end our lesson early unless somebody has some questions to ask. So amines have this amino functional group, this NH2 functional group. They're derivatives of ammonia. Ammonia is NH3. This is NH2. And you have the suffix amine. So whatever it is, you put an amine at the end. If it's 3 carbons, it's a propylamine. If it's 4 carbons, it's a butylamine. 5 carbons, it's a pentylamine. And that's how you name them. The longest, whichever is the longest alkyl that's attached to the nitrogen amino group is the parent alkane. And what you have to remember is that this nitrogen has is electronegative. And the carbon nitrogen and the carbon and the nitrogen and hydrogen bonds have some polarity, they're polar. But as you, of course, as you increase the length of the hydrocarbon chain, as this oily part, I should say, this part is not very water soluble. This part is quite hydrophobic. As this end gets longer, then the solubility of the amine will go down, because then you're getting the longer hydrophobic, not water liking, water hating tail. I think I'm hoping all of you guys are familiar with the term hydrophobic and hydrophilic. Judy, Sasan, and Shadisa, are all three of you familiar with the meaning of hydrophobic, hydrophilic? Have you covered that in previous chemistry courses?
Well, I study chemistry back home. I don't
Uh-huh.
know what does that mean in like my language, but I
Okay.
don't know. No, I'm not
Okay,
sure.
so thank you so much for bringing that to my attention, because I don't want to be saying things and using terms that are meaningless to the students. So hydrophobic and hydrophilic. So hydrophobic, in English, the name phobic or phobia comes from the meaning of having fear. When you have a phobia of something, that means you're scared of it. So if you are hydrophobic, it means you don't like water. Water is not your friend. You're not very water soluble. If you're philic, if you can think of it as the philic, the lick part reminds you of like, you like it. So if you're hydrophilic, it means you like the water, you're water loving, you're not water hating. So these hydrocarbon tails, these parts, they're hydrophobic. They're not very water soluble. They're not water loving. These tend to be kind of having more waxy, oily, greasy kind of consistency. So if you can think of it, this would be what you would find in like oils. And so these hydrocarbons would be hydrophobic. These are not water loving ends. So that's why if you get longer hydrocarbon chains, as the tail gets, this chain length increases as it gets longer, they become less soluble, because then you have more of this hydrophobic character, more of that part making up your molecule. As that part increases and gets longer, well, guess what? You're not going to be as soluble as a shorter one. Did that make sense to all three students?
Yes.
Yes?
Yes.
Okay, perfect. So yeah, the concept of philic and phobic. Hydrophobic means water fearing, water hating, water don't like it. And hydrophilic is water loving. Okay. And yeah, I think we oftentimes consider that that term, so-and-so has a phobia of spiders. They're afraid of spiders. So-and-so has a phobia of tight spaces. Or so-and-so has a phobia of crowds. They're agoraphobic. They're afraid of being outside in crowds. So that phobic, that phobia, is the same term that is applied to in chemistry as well, in terms of hydrophobic, hydrophilic. And finally, we're going to touch quickly on amides. Again, we're building on these. So amides are very similar to the previous molecule of carboxylic acids that we discussed earlier, except that we have now sort of something in between a carboxylic, a carbonyl group, and then this amino group that we had in amines. And together, when you have these two present, you have what is called an amide. Contains the COO and an N, and the nitrogen group attached to two other functional groups, which can be hydrogen atoms, or it could be alkyl groups. So these R's at this end could be just hydrogens, or they could be more longer hydrocarbon chains. And the way you name these amides is that you again take the parent acid name, just like we did for what was it, esters here. You take the parent acid and you replace the oic part with amide. So for example, methyl, instead of it being methanoic acid, you make it a methylamide, for example, here, or ethylamide, or propylamide, butylamide, pentylamide. That would be how you would name amides. And I think that covers everything here. I hope you're now able to attempt naming some of these structures. Go ahead and try some of the support questions. Try naming some of these groups. If you have trouble, definitely refer to your textbooks section on naming these kinds of organic groups and functional groups and how to use the IUPAC naming system. It will definitely be a good guide. If you have any questions, though, that you feel like this textbook isn't providing enough support for you, or you would just rather have me explain to you, please feel free, contact me by email. We can always try and solve it through email, or if sometimes in previous years, students have contacted me and we've either talked more about something a few minutes before class started, or sometimes stay on after class has finished, and we can talk about it one-on-one and smooth out any wrinkles, any questions that you have. But don't let questions linger too long, because with every lesson, we build on what was previously taught and what was previously learned by you. So that's my biggest advice to you, is don't fall behind, keep up. And if you have any questions, just don't hesitate, shout it out, ask right away, and we'll try our best to answer those for you. Okay, any questions at the end of today's lesson?
No question.
Okay, thank you so much. So I will see you Wednesday, where we will continue with lesson number 7. Okay, thank you very much, everyone. Have a great evening.
Thank you. Have a good night.
Great night. Bye.
Good night.
Bye.